Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis, and today we are going to talk about the InSight mission. And for this, we invited the Deputy PI of the mission, Sue Smrekar. Hello, Sue, how are you?
Hello, I'm doing well. How are you?
I'm good. Good to see you again. But this time we're
You?
not going to talk about Venus. We're going to talk about Mars.
What?
So Sue is, as I mentioned, Deputy PI of the mission. She's also the lead of one of the instruments in the US for InSight. So before going through the details, I just want to mention that InSight is a mission launched by NASA, which landed on Mars and had the goal of determining the internal structure, basically, of Mars. So Sue, to our viewers, I'm sorry, I've not not done this for like a month, so I'm rusty a little bit. Remind us, tell us where you're watching us from, and we are going to have a conversation for like 10-15 minutes, and then we're gonna take some questions from you. So if you have any questions for Sue or myself, please post them on your social media. We will take the time to answer to some of them. So Sue, let me know a bit, what is really InSight?
InSight is the first mission to focus on understanding what's going on beneath the surface of Mars. You can think of what goes on under the surface as like the engine for the planet. It drives the geologic activity, it helps form the atmosphere, it shapes the climate. And so understanding what's beneath the surface of Mars is a super important objective.
So for this, you cannot dig or go in the interior of Mars, right? So how do you find out about the interior composition of a planet?
Yeah, well, one of the ways we kind of explained our mission is by saying we take the heartbeat, the pulse, and the temperature. As a physician, we look at things that we can measure at the surface to interrogate what's going on inside the patient. And in terms of the heartbeat, what we're really doing is listening for seismic waves. We have a lander. It's not a rover. People are used to rovers on the surface of Mars, but InSight just sits kind of zen-like on the surface and waits for seismic waves to travel from some remote event to our lander, to our seismometer, which was placed on the surface of Mars. And so, it's kind of like a sonogram. The waves start out somewhere else and they travel through the layers inside of Mars. And from that, we can get the thickness of different compositional layers, the crust, the mantle, the core. And those tell us really important things about how the planet formed initially and how it's changed over time. And then the another instrument we have is called RISE, and it's like a geodesy experiment. Basically, it's really aimed at trying to understand the size of the core. And so, one of the big questions is, was the core liquid, solid, partly liquid, solid? And we get at that question by determining very precisely the motion of Mars. We send radio signals back and forth to Earth to measure that position. And it's like if you take a raw egg or a cooked egg and you put them on the table and you spin them, you just rotate them really fast, they spin differently. And that's basically the concept of how we get at the core. So that gave us the size of the core and told us that it's liquid. And then we tried to take the temperature, but that's maybe a longer story.
We're gonna go back to that. I want to have more information about this. But before this, we have people watching us from Strasbourg, Virginia, not the Strasbourg in France, Colorado, Grass Valley, California, Portugal, Scotland, Denmark, Buffalo, New York, Sydney, Australia, Central New Jersey in the US, Italy, Quebec, I was there recently, Woodlands, Texas, Stockholm, Milan, Italy. So welcome. We are talking about the InSight mission and some of the success of the mission and what's going to happen in the future. So this instrument that you briefly mentioned, is called H3P. That's what it is, right?
Yes. the heat flow and physical properties probe.
Okay, so this was an instrument that was supposed to go in the surface of Mars. I mean, we always talk about success. So I want us to talk a bit about the complexity of doing those missions. Maybe you can use this as an example or surprises or that we had when we launched this mission, when we basically tried to dig into Mars. Can you tell us the background?
Sure. So the HP cubed instrument was built by the German Space Agency, and its goal is to see how much heat is coming from the inside of the planet and traveling through to the surface. And that's a super important measurement because it tells us about not only the temperature under the surface, but also just the original amount of radiogenic elements like uranium, thorium, potassium that give off heat over time. And so, and you think about, how much focus there is on Mars about trying to understand, is there liquid water at depth? And so we'd love to know exactly, how deep would you have to go to find liquid water? And so that's part of the questions we were trying to address. And so to do that, to take that temperature of Mars, what we wanted to do is get down to about 3 meters depth, about 10 feet down, and have a string of temperature sensors that we would pull behind what we call the mole. Mm-hmm. And we were going to take the temperature, so we had a temperature gradient, and we were also going to take the thermal properties of the soil underneath the surface to get the heat coming out. It basically, this mole, it looks like a great big long nail about this long, 30 centimeters, and it's like a miniature jackhammer. It has like a hammer inside that hammers it internally. And we did a ton of testing, try to understand to our best ability how to make that work on Mars. But, nothing had ever been under the surface of Mars before.
Yeah.
And we had some indication of what to expect near the surface from the rovers. People have looked at the tire tracks from the rovers, and, there've been small little drills and so forth. But so we had an idea of what to expect, but not a precise measurement. And so it was placed on the surface and started to hammer with great guns. It functioned properly, but then the soil that we encountered was different from what we anticipated. And if you've ever taken a hammer and whacked it on the table, it has a recoil or a nail or anything. And so this hammer has a recoil, and it relies on friction, the soil against the side of this mole, to resist that recoil. Mm-hmm. But in this location, the soil was different, and it had a very brittle, thick layer at the surface, and the soil didn't come against the sides of the mole mechanism the way we expected. So it wasn't able to stay under the ground. This recoil from the hammer caused it to pop back up. Yeah. So we tried many different things, and in the end, we're not successful in making it, go fully underneath the ground. It was a very sad and frustrating experience, but that's part of exploration. We don't always know ahead of time what's going to happen.
Yeah, so let's talk about positive side of this mission. I mean, there was some very extraordinary results, like the detection of Mars quakes, for instance. So can you tell us what was done in this field specifically?
Sure. So, we met almost all of our science objectives. We came up with a good estimate of the thickness of the core, which tells us about what it's made out of, the elements inside the core. We came up with a good estimate of how the temperature inside the mantle, deep down, the thickness of the compositional layer near the surface, the crust. It seems about 45 kilometers. There was just a huge range of ideas of how thick it was before that, and similarly with the core. So we were able to get very good estimates of all those things. And one of the for me and for many people, one of the most exciting things was finding activity on these series of faults that are associated with like some of the youngest volcanism on Mars, between about 2 and 10 million years ago. And we can get those ages of these huge volcanic flows from counting the number of impact craters that sit on top of those. And so, before the mission, we had an idea that this area is geologically young for Mars. But we just never anticipated there would be so much seismic activity in these faults. And, people are now looking to see, can they see evidence actually of motion on these faults, in images. And, there have been some images that say, well, there's some dark material near some of these faults. Maybe it's a volcanic vent. Maybe we're actually seeing stuff spewing up from inside and falling on the surface. And there's just so we know that Mars is a very old surface in general. And on average, it's billions of years old, right? So to have discovered this place where there's so much seismic activity and comparatively recent volcanism, and maybe even some things, at least particles coming out today, that was one of the very exciting aspects of the mission.
Yeah, it's an exciting aspect of the mission because when I did my master in planetary science, I remember they keep telling us that Mars is a dead planet. Mars has no volcanic activity. And at the end, this mission revealed that Mars has indeed still some volcanic activity. And for us, it's interesting because volcanic activity implies some possible complex interaction with the atmosphere, like the presence of methane, maybe due to the volcanic activity, for instance. So that's a very interesting result, definitely. We have people joining us from various places in the world, and I just want to mention a few of them: Washington State, South Florida, Ohio, San Jose, California, Hermosillo, Mexico, Alaska, Arizona, Louisiana, and that's all. We also start having questions. And yes, behind me, that's Lamar. You have seen this in the previous SETI live. At the SETI Institute today. So we're gonna take a few questions from the audience. But so now we have all this information about Mars, right? Can we say we know better the interior of the planet, and how this information will be used in the future?
Yeah, we definitely know more about the interior of the planet. One of the things, of course, people are interested in studying Mars because they want to understand its potential for past life, potential maybe for humans in the future and so forth. And, many of the things that we're studying and have learned about help us better understand, the long-term prospects for that. When would it have been a good environment in the past? What are the conditions today? For example, the core. We know that at one point in the past, billions of years ago, Mars had a magnetic field. And so that would have been, convecting inside the core. And now we have a pretty good idea of the composition of that core. So we can better understand what kind of dynamo it might have had, what that magnetic field might have been. And in addition to our measurements of the size of the core, we also had a magnetometer on board. And Mars already had these kind of crazy parts of the crust that were magnetized from billions of years ago when there was a dynamo. And from that magnetometer on the surface, we discovered that, in fact, that crust has an even stronger magnetic signal than we anticipated. So it says there's a lot of variation in the magnetic field from, that's left over, these basically tiny little magnets, pieces of iron minerals inside the rock, that creates its own miniature magnetic signal. And so, we learned about the very early history and how the surface of the planet might have been shielded, from incoming radiation and particles from the sun. So that was one of the things that we learned, and getting a better idea about the temperature. We don't have the heat flow measurement, but by better understanding the structure, we can get a reasonable estimate about temperatures underneath the surface as well. So yeah, we've learned a lot more about both temperature and about what it's made out of.
Right. So what's the status of the mission? I mean, we entitled this Farewell InSight. So what's going on with the
Yeah,
mission itself?
yeah. So we were we are a Discovery class mission, which is one of NASA's smaller categories of mission. So far less expensive than the big rovers, and so we had to be very cost conscious in our approach. And so we used some solar arrays that were similar to those who have been flown before. And we definitely, met our science objectives and lasted longer than we told NASA we promised them to. So we've gone past our warranty. Of course, we hope to keep collecting more and more data, but right now there's a lot of dust on these solar panels. If you go to our website, you can see images of how it's accumulated over time, and it just looks super dusty. On all of the other missions that have gone to Mars that have lasted a long time, they got lucky. Basically, they had these dust devils. They basically had these turbulent wind features that cleaned off their solar rays. All the dust was gone after these things came past. And we can tell from our pressure sensors that these wind features have passed close by, but not right over the lander. And so they did not clean the dust off. So of course we were hoping that this would happen. We didn't, it's not a success criteria to keep going, but of course we wanted to keep collecting more seismic data. So we could, have so much dust that we don't have enough power to keep going kind of any time. We anticipate at least another couple months of lifetime. And we're operating at very reduced levels, only the seismometer on about a quarter of the time, all the other instruments off to save power. And we could still see a miracle and have a cleaning event. It could happen, but we're not counting on it. We haven't seen it in the 2 years that we've been there, so most likely we have a couple months to go.
Some people pray on Earth to get rain. You are praying to get a dust storm onto your spacecraft on Mars. So yes, you have a little bit more data coming. So what yes, kind of data do you expect coming from an potentially extended life of this mission? Why is it important?
Right. Well, it's important for a variety of reasons. I mean, we saw the energy really declining over the last 9 to 12 months. And, in these last, say, 6 months, we've gotten some really big events. And so like our biggest event ever, seismic event, seismic magnitude, like 4.7, we got that quite recently, maybe I think about 5 months ago, perhaps. And so, so not only could we get other big ones, but the more quakes we have from different locations, the better we can define what's inside the planet, because we can tell that there's some variation. It's not completely uniform. It's not completely, the crust is not the same thickness exactly everywhere. There's different, the crust, how the crust is broken up by impacts gives us a different signature. In fact, the other crazy thing is that we had been planning to listen for the signature of impacts on Mars, meteors striking the surface, and like in the first couple of years, we just didn't see any, and then we had almost 3 in a row. So we're like, where are the impactors? We know that they strike the surface of Mars. And then, some weird statistical thing happened, and we got 3 right almost in a row. And so, the more events from different places, the more impacts, it basically gives us a way to kind of build up incrementally a better and better model. It gives us better information about the velocity of the seismic waves, the variations from place to place. So we hope to just eke out a little bit more detail about what's going inside.
All right. Before we go to one of my last questions, I see that Charlie Doyle asked a question about the probe. I don't know if you can show the question from Charlie, but I will read it. Do you think a redesigned lander could successfully dig a probe deeply into Mars?
Yeah, I think that the design that we had could be improved upon. For one, we would make sure that we could essentially have something that would give a little bit more force on the back of the probe until it can get deep enough so that the friction is going to hold it in place as it hammers. We tried that to some extent with our rover's robotic arm, and it was never designed for that at all. And we couldn't push exactly on the probe, but if there were a way to give it just a little bit more force, because it's not a huge amount of force that causes it to back out.
Mm-hmm.
So if we could just have something, if we could have something that's the equivalent of a person standing there and pushing on it a little bit until it gets down there, that would certainly allow it to get to a point where it has enough friction that it can keep hammering on its own. Because it initially hammered right in and worked very effectively, but in that particular soil where the hole got bigger instead of the soil collapsing around it, it didn't have enough friction. So I think we could certainly redesign it to be effective.
Okay, so we have one question from Maria Tseng, if we can show it. She's asking how we can generalize from your data collection site to the rest of the planet. So basically, how from the data you get from this area surrounding the InSight, you can make an assumption for the entire planet.
Yeah, so in addition to this kind of data from past orbiters, we have basically the gravity field. So we can use the gravity field to discern the variations in density inside the planet. So, for example, if we want to think of the crust as being a layer, we can see from the gravity that has variations in it. It's thicker. The crust is in fact thicker in the southern half of the planet than in the northern half, and we can tell that from the gravity field. So basically, what our mission did was provide an extremely important reference point, because what we didn't know from the gravity field is what the exact density variations were. Basically, we didn't know how much less dense the crust is versus the underlying material. And now with our mission, we put a pin in that reference. And so we now know that underneath our lander, the crust is about 45 kilometers thick. And so from there, that gives us the point at which we can shift up or down that gravity field reference of the estimate. We estimated crustal thickness globally before, but it had an error bar of like a factor of 2 or 3. And so now that error bar is gone, and we know precisely the depth in one location, so we can extrapolate it all around the rest of the planet.
Okay. Another question that we have, but I'm going to correct the questions, from Fern Lovebomb, who wonder if you can see a time-lapse video of showing not the lenses got dirty, but the solar panel getting dirty. Do you have something like that?
Yes, it is on our website. You can definitely find it on our website.
Okay.
And if you follow us on Twitter, there was a recent one on Twitter too that showed it just getting dustier and dustier over time.
All right. Can you remind us the thickness of the Earth's mantle, the Earth's asthenosphere? Yeah, crust.
Yeah. So kind of like on Mars, there's two different groups of thicknesses. So under continents, the crustal thickness is about 40-50 kilometers, and but under the oceans, it has a different composition, and it's formed in a different manner. So under the oceans, it's about say 5 to 12 kilometers thick. So portions are much thinner, and some portions are thicker on Earth relative to Mars.
Okay, so a bit some kind of the future of this field of research. What's the next steps? what are we going to do?
Well, the next mission that's planned is set to acquire, it's going to be another big rover mission, and it will acquire samples on the surface of Mars. And the Mars is called the Mars Science Laboratory, and it's going to, sorry, not Mars Science Laboratory, but the next rover will take these samples and, Mars 2020 rover is taking samples right now, and then the rover that is going to be sending them back is being built. And so they actually just put out a new idea for this architecture. There's going to be multiple elements. There's a rover that sits down, and the intent is to go and pick up the samples from the Mars 2020, and then then there's another piece that will is a rocket that is meant to, the samples are meant to be placed inside the rocket and launched back to Earth. And now I just saw that they are considering having a couple of helicopters that are sort of like the backup to the rover. Like if the rover, can't find these samples or needs help getting the samples, they're talking about putting a couple of little helicopters on board as well that can assist in that process of acquiring the samples collected by the Mars 2020 rover. So it's a very major undertaking to bring these rocks back from the surface of Mars, these carefully selected rocks designed to try to answer very specific questions. So that's the next really big thing. And then of course people are thinking about all kinds of things like we would love to be able to try getting heat flow again near these areas that I said are recently volcanically active, these faults. So, people have ideas for all kinds of fantastic Mars missions, but the next one that's in development is this one to bring back the samples.
Yeah, I think I'm reading the comments here and people are making comments talking about the probe and so on. I don't know, the complexity of having helicopters flying and being controlled on Mars. I mean, it's something extraordinary that we are now talking about this.
Yeah.
It's not, we are talking about a planet far away, millions of miles away from us, and helicopters that will control themselves basically to be able to find samples and analyze the surface of the planet. I mean, it's remarkable the progress we made over the past 30 years in robotic exploration of the planet. And Mars missions are truly the lead into this. We basically did most of the experiment possible on the Mars surface.
Yeah.
And that brings me to a question that from someone, I saw it, but I can't find it. Someone asking, are we going to use the same technology one day to explore the cave of Mars? Is there any project to do something like that?
I'm sure someone somewhere is thinking about that, but I don't know of a specific mission concept yet. I know that there's a concept to explore caves on the moon, where this little kind of wheeled vehicle is kind of rappelled down into the side, and to take measurements as it goes. Moon diver, I believe the concept was called. But I haven't seen a similar thing applied to Mars, but I'm sure that kind of technology would work.
Hey. Well, thank you very much, Sue. So what's the next step for you? What's the next big step in your career?
For me, on to the other terrestrial planet, Venus. So yeah, I'm leading a mission to send an orbiter to Venus to really get high resolution topography, radar images, composition, core size, all that great stuff. So it'll it's first mission designed to study the surface of Venus in over 30 years. So we just have made great technological leaps in that 30 years too.
Yeah, it's exciting that we are going to finally go back to Venus, explore the surface of the planet, do some measurements of the atmosphere, and kind of better understand this planet, which is radically different to ours and radically different to Mars, of course. Well, thank you very much for your time. Sue. We
My
see
pleasure.
you soon for another SETI Live on Venus, maybe, or something else.
Sounds good. Thank you.
For all our viewers, thank you very much. This was a SETI Live from the SETI Institute. I remind you, we are a non-profit organization. We rely on your donation that you can make by visiting our website at seti.org, give now. Or you can also support us by first sharing this video, giving us some thumb ups, commenting, asking questions. We take the time to answer to some of your questions if you write to us. But you can also join our social media. We are on every platform, Twitter, Facebook, etc. And finally, if you want to get some news regularly from the SETI Institute and learn about the remarkable work that we do here at the Institute, you can join. You can also sign up for our e-news. The link is appearing magically while I'm talking. I love that. So thank you very much to everybody watching us from everywhere in the world. I forgot to mention we have people from Australia as well who join us. So, and we will see each other next week for SETI Live on moon bases, if I remember. So stay tuned, join us, comment, talk about planetary exploration to your friends. Okay? Bye-bye. Thank you again, Sue. You take care.
Bye-bye.